So today we're going to continue our discussion of the derivative and talk in particular about ways that we can find derivatives of functions without having to resort to the actual definition of the derivative. And somewhere along the way we will get to the question of what these people in the picture are and what they're doing. But before that, let's talk about the basic idea of the derivative. We will find out how to take the derivative of a constant function, how to use rules for differentiation like multiplying a function by a constant. How does that change the derivative of the function? Adding two functions, how can we compute their derivatives? Subtracting two functions, and also the derivatives of the trigonometric functions sine and cosine. So let's remember what we're actually discussing. The derivative of a function at a point a is the limit as h goes to 0 of f of a plus h minus f of a divided by h. Another way to write the exact same limit is to say it's the limit as x goes to a of the quotient f of x minus f of a over x minus a. So there's two ways to think about a difference quotient as the denominator of that quotient gets smaller and smaller. One way is to say let x get closer and closer to a, then their difference will get closer and closer to 0. Or we say take a number a and then move it over by a small number h. These two limits are computing the exact same thing, and if that limit exists, then we say the function is differentiable at the point a, and that limit we call f prime at a. So this derivative is what we'll be studying and using for the entire next couple of chapters of the text. The derivative measures the slope of the line which goes through the point a comma f of a and which is tangent to the graph of the function. The derivative also measures the instantaneous rate of change of the function at that point. This is very useful if the function is something which is changing over time, but also things which change relative to space can be used, the derivatives can be used. We also know that the derivative produces the best possible linear approximation to the function near that point. So many different perspectives on what the derivative can actually do for us. We have many ways to write the derivative because it was actually developed independently by two very important mathematicians. Isaac Newton was the first to come up with the idea of the derivative, although he didn't call it the derivative, he called it the fluxion. And so his is the name fluxion, which we don't actually use anymore. He also came up with this prime notation. So if we use f prime of x or y prime of x or just y prime to talk about the derivative of a function, then we're using Newtonian notation. Now Leibniz was the other mathematician who came up with the ideas for calculus. Actually only came up with it about 10 years after Newton did. But as you can see, his notation is entirely different. His intuition was also entirely different, and the way he expressed his derivatives was in terms of a fraction of infinitesimals. So he called it a dy, an infinitesimal number, and divided it by another infinitesimal number, dx, and the quotient was the derivative dy dx. So we can say dy dx, or d by dx of f of x, or just df dx. So Newton was the first person to come up with this. He uses the prime notation. Leibniz was the second, and the word derivative comes from Leibniz, and also the Leibnizian notation for the derivative. And they're linked by looking at the definition. The derivative of the function at the point x can be expressed in terms of this limit. The limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. What's changed from the previous times I put up the limit definition of the derivative? Well, I used to have an h here. Now I'm calling it delta x. And the numerator, f of x plus delta x minus f of x, is the change in the function values across a small change in the function inputs. So it's the change in the y values after you move x by a small amount delta x. So this difference quotient can also be written as delta y divided by delta x. It represents the slope of the secant line connecting 2 points on the graph of the function. The first point being x comma f of x, and the second point being x plus delta x comma f of x plus delta x. So delta y divided by delta x is an actual slope of an actual line, and in the limit it becomes the derivative. So what we have is a nice connection between the limit of a finite difference quotient and this infinitesimal. All right, Leibniz liked the idea of infinitesimals. We don't actually use infinitesimals because they don't represent actual real numbers. But it is quite useful to think of dy divided by dx as a quotient, even though we're not actually dividing any actual numbers. Some of the theorems about derivatives are more recognizable when we write them in Leibniz notation because Leibniz notation suggests them. So that's one reason that we like Leibniz notation. We took a few of the derivatives in the previous class, and let's take a look at how those went and also what we can interpret from the derivative. So first function that we'll study is f of x is x squared, and in the last class we used the definition to find f prime of x. Here's how it went. Computing the derivative from the definition always amounts to writing down the limit of a difference quotient. In this case, we want the limit as h goes to 0, f of x plus h minus f of x divided by h. Now what is f of x? F of x in this case is the squaring function. So f of x is x squared. F of x plus h is x plus h squared. And this is the thing that we want to find the limit of as h goes to 0. Now whenever taking the limit of some algebraic expression, the first thing we should always try to check is, can we just plug it in? Can we just plug in h equals 0 in this quotient? And the answer is no, we can't, because the denominator is h, and if we plug in h equals 0, the denominator is 0, and we don't have a limit law for limits where the denominator is 0. Does it mean that the limit does not exist because the denominator goes to 0? Actually, no, that's not true either, because if you look at the numerator is also going to 0 as h goes to 0. Because as h goes to 0, the first term, x plus h squared, becomes x squared, and then we subtract from that x squared, so the numerator does go to 0. So this limit is of the indeterminate form 0 over 0, and in those situations anything can happen. What happens here? Well, we can find that by multiplying out the numerator and simplifying it. So when we take x plus h and square it, it becomes x squared plus 2 times x plus h squared. And I subtract from that the x squared, which is waiting for it right there. Now I've crossed out already the x squared and the minus x squared. You can see that these are going to cancel. So I can simplify my quotient as 2 times x times h plus h squared divided by h. And what I notice now is that every term is a multiple of h. I can cancel an h from each of the terms in the numerator, leaving 2 times x and then 1 extra h. And canceling the h from the denominator leaves a 1. So this quotient then reduces to just 2x plus h. And now what I see is not a quotient where the denominator goes to 0, but a simple polynomial, and there's no problem with just plugging in h equals 0 to a simple polynomial. When I plug in h equals 0, the 2x stays because it doesn't have an h in it, and this term goes away. What's left is 2x. All right, so what we've discovered is that f prime of x is 2x when f of x is x squared. Now there's nothing to stop us from taking that derivative and finding the derivative of that derivative. After all, the derivative is just another function. When we think about the derivative of the derivative in relation to the original function, we're calling it the second derivative. And the second derivative measures, if you like, the rate of change of the rate of change of a function. We'll look a lot at what the second derivative tells us about the shape of a graph of a function later on in Chapter 4. Leibniz notation for the second derivative, we will write d squared y divided by dx squared, or d squared divided by dx squared of f of x, or simply d squared f divided by dx squared. I would say that the first use of Leibniz notation for the second derivative is the one that's most common, and then also just using the double primes in the Newtonian notation. So let's take a look at the graphs of these functions, including the graphs of the derivatives of the function. The first function we started that with was f of x equals x squared, and we know that that's the function with the simple parabolic graph like this. Okay, so that's not surprising. The derivative, 2x, the graph of that is going to be a linear function. And let's look at the graph of the function and the graph of its derivative and verify what the derivative is telling us about the graph of the function. For instance, when x is negative on this side of the plane, we see that f is decreasing. And a decreasing function is going to have a negative derivative. Decreasing function, negative derivative. Now, to the right of the y-axis, when x is positive, we see that the function is increasing, and an increasing function is going to have a positive derivative. And that's exactly what we see on this side. Now, to be perfectly precise, it's actually true that an increasing function has a non-negative derivative, and a decreasing function has a non-positive derivative. And also, whenever there's a horizontal tangent to the graph of the function, we will have a place where the derivative is 0. That's exactly what's happening at the point x equals 0 on this graph. When we throw in the second derivative, well, what is the second derivative of f? It's the derivative of f prime. F prime, we see that the graph is a linear function. And the linear function, what's the slope of the line tangent to the graph of a linear function? Well, that tangent line would be the graph of that function itself, so the slope of the tangent line is the slope of the original function. What that tells us is that the second derivative, the derivative of this linear function, is a constant function, that constant being the slope of this line. So f double prime is a constant, its graph is a horizontal line. And that makes sense because a linear function grows at a constant rate no matter what x is. So the rate of change of a linear function is always the same. So then let's kick it up a notch. Now we'll look at the cubing function. Not before, but let's see what similarities we can find. As before, when taking the derivative by definition, we should write down the definition of the derivative. Okay, and now the function does something different. Instead of squaring its input, it's going to cube its input. Can I plug in h equals 0? No, because the denominator goes to 0. What about the numerator? Numerator, well, x plus h is going to go to x, so x cubed minus x cubed. The numerator also goes to 0. So this is an indeterminate form, a limited indeterminate form, which means that we cannot just plug in. But what we can do is expand. Let's expand that numerator. So most of you probably remember that x plus h quantity squared is x squared plus 2x h squared. Maybe you don't remember, but that's why I'm here. X plus h cubed is x plus x cubed 3x squared h, 3x h squared plus h cubed. Okay, and from that we subtract the x cubed, which comes up. And what do we see? Well, we added something and then we subtracted it. So we can just cancel those off. And what we get next is the 3 times x squared times h, 3 times x times h squared, and the h cubed. Again, everything here is a multiple of h. So there isn't any problem with canceling the h in the denominator with one h in each of the terms in the numerator. And that's great because now what we have is a polynomial. We have canceled out the precise thing which was giving us trouble in computing the limit. So there isn't any impediment now to just plugging in h equals 0. What I get is 3x squared. Okay. Any questions about that one? You know, if you wanted to do it with the other form of the limit, the f of x minus f of a over x minus a, you will still have a limit kind of like this to do. The exchange you make is that instead of having to expand x plus h quantity cubed, you will have to factor x cubed minus a cubed. All right, so expansion or factoring, take your pick. All right, now let's take a look at, here's the good cubing function. And let's compare it with its derivatives. Okay, again, we've got an error on the left-hand side, but the right-hand side looks good. This function is increasing. This function is positive. And that's what we would expect. The further out we go here, the more positive we get there. The function is increasing all through the real numbers, even at 0 here, even though its derivative is 0 there. And that's one important distinction we made last time. It's not necessarily true that if a function is increasing, its derivative is positive.
well, we said that if a function is increasing, its derivative is non-negative. And then we do see that. Okay. And here's the second derivative. This function is increasing, so its derivative is positive. What's not entirely obvious is that this function kind of looks like the squaring function, and its derivative looks like a line. Okay. So, is it all as easy as that? Well, let's take a look at a few other power functions, such as the square root function. Square root function is a power function if you take a power to be 1/2. So what do we get with the definition of the derivative here? Okay, well, starting from the definition, we can only write down one thing, and that's a limit. Then the only thing we can do is write down what our function does, and in this case, our function is the square root function. Okay, now we played a little bit with limits that had radicals in them. If you remember what you can do to a limit like this to try to evaluate it. Rationalize it. By rationalize, do you mean multiply numerator and denominator by something to make the radicals in the numerator go away? Yeah, okay. So it doesn't turn into a rational number, but it does turn into something that we can evaluate. Multiply the numerator and denominator both by the conjugate radical here, x plus h square rooted plus x square rooted, divided by x plus h square rooted plus x square rooted, because you can't just multiply by anything and have the same thing. You can only multiply by 1. So multiply and divide. Okay, and now what we get is a difference of the square of x plus h square rooted and the square of x square rooted. Well, what is the square of the square root of x plus h? It's x plus h. What is the square of the square root of x? That's x. Now again, I have two things which cancel, leaving me an h in the numerator and a multiple of h in the denominator, which is great because the denominator going to 0 was precisely because of the h factor, and it cancels. It cancels away. This is going to be 1 in the numerator. That's going to go away. And now there isn't any problem with letting h be 0. So what do I get in the derivative? I get a square root of x here. I get a square root of x here. So the derivative is 1 over 2 times the square root of x. Okay, and if you wanted to do it in the square root of x minus square root of a form, here you really do just have to do the same kind of algebraic manipulation. Okay, so that's related to a technique in arithmetic called rationalization. We don't have a rational function here, but you do multiply and divide by the conjugate radical. Questions about that one? All right. Well, you guys are swallowing this all. That's good. Let's take a look at the square root function. Here is a graph of it. Remember that the square root function is the inverse of the squaring function. Squaring function's graph is an upward-facing parabola. The inverse is going to rotate or reflect that graph, and so you have an outward or rightward opening parabola. That's the square root function. And let's take a look at the derivative of the function graphed here. Well, what sign will the derivative have? It'll be positive because this function is increasing. Where is it increasing more? Is it increasing at point A here or point B out here? Point A. So the derivative here is going to be larger than the derivative out here. And the closer I get to 0, the more my derivative is going to get. If you can see my little remote here, I'm trying to hold it tangent to the curve. And how much that remote is pointing up or down, that's the sign or the size of the derivative. So very positive derivative, somewhat positive derivative, just a little bit positive derivative. So the graph of the derivative should be very large when x is close to 0, and then taper off. Okay. So how about this next example here? F of x is the cube root of x, which we can also write as x to the 1/3. How would we find its derivative? Well, again, there's only one thing to do here, and that's write down the definition of the derivative, and then use whatever f is doing on that function. So I want x plus h to the 1/3 power minus x to the 1/3 power. Okay? And these cube roots are kind of like radicals. They're radicals of a different power. They're cubic radicals. And so we can try a similar technique to simplify this fraction in such a way that I can compute it without having a 0 over 0. Trouble is that you just try the same trick you did before, where you convert this to a plus and you multiply by that thing divided by that thing. It's not going to cancel out like you want. The conjugate radical in the cube root case is much nastier. It's this. Whoa, yeah, right. Okay. So if this is a minus b, then the conjugate radical is not a plus b. It's a squared plus a times b plus b squared. Why is it that? Well, that's the thing that if you multiply it by a minus b, you get the cube of a minus the cube of b, which is exactly what we want. We want to be able to cube x plus h to the 1/3 and cube x to the 1/3. So we get x plus h minus x. So they cancel just like they did before. Thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our like they to our like they did thanks to our this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, this, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our code, like they did, thanks, this, thanks to our code, like they did to our, like they, thanks, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, like thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, like they did to our, thanks to our, this, thanks to our code, thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did thanks to our this like they to our they like they did like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our they like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they did thanks thanks to our this like they to our like they thanks thanks to our this like they to our like they thanks thanks to our like they did to our like they thanks thanks to our like they did to our like they thanks thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they thanks to our like they did to our like they, thanks to our thanks to our code, like they did to our like they, thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like to our code, like they did to our like thanks to our like so any positive whole number, we're saying that the derivative is going to be that power times the one lower power function. Well, just look at what we did before. We want to expand x plus h to the n, and we know how to do that. It's x to the n plus n times x to the n minus 1 times h plus a whole bunch of stuff with at least two h's in it that we don't care about. If we subtract x to the n, well, the x to the n is going to go away, and I'll have n times x to the n minus 1 times h plus, again, stuff with at least two h's in it. Divide that by h, I have a factor of h. I have two factors of h. So when I cancel, I get n times x to the n minus 1 plus stuff with at least one power of h. And if it has a power of h in it, then letting h go to 0 will make all of this stuff, this garbage that I'm not writing, go to 0. What doesn't go to 0 is the n times x to the n minus 1. Okay, so it's a consequence of Pascal's triangle that the derivative of the power function x to the n is n times x to the n minus 1. I'm not sure how Leibniz figured that out, because Leibniz came before Pascal. But that's how we do it now. Questions about the power rule? Okay, well, awesome. So now we've established that for whole number powers. How about constants? Well, constants are actually very easy to find the derivative of. The derivative of a constant function is 0. And if you want, you can think about this as kind of a power rule application itself, because x to the 0 power is 1. All right, so if you think about 1 as x to the 0 and apply the power rule to it, then you can say, oh, well, the derivative of x to the 0 is 0 times x to the minus 1, and 0 times anything is 0. It seems very satisfying, right? Only trouble I would have is that x to the minus 1 isn't defined when x equals 0, and 0 is always defined. So they're not equivalent at 0. But, you know, if you want to use that in the thought bubbles to think about why the power rule is true even for constants, then you can do that. Other ways to talk about this is, well, you can just apply the difference quotient. F of x plus h is that constant. F of x is the same constant. So the numerator of the difference quotient is identically 0. All right, and that's different from saying that the numerator tends to 0. The numerator is always 0. And so the difference quotient is always going to be 0. And so the limit of 0 as h goes to 0 is 0. Hence, the derivative of a constant function is 0. Or you can just think about it graphically. What is the graph of a constant function? The horizontal line. And if the derivative is supposed to measure the slope of the tangent line, then we would be looking at the slope of a horizontal line, and the slope of a horizontal line is 0. Right? So many ways to think about that. Cool. Okay. So now what we get into is what we call the calculus of derivatives. And so the whole subject of calculus, I think, takes its name from the calculus of derivatives. The Romans used these little boxes of rocks to do all of their mathematical arithmetic. And so the word calculus means rock. And so this is their early calculators. And we're going to use a calculus, a system of rules, to find derivatives. So the word calculus means system of computation, and it comes from rock. Okay. So like before, we proved basic limits and then limit laws. Now we have basic derivatives, and we'll prove derivative laws. We had the limit laws, which said that if you have two functions that have a limit, the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of a multiple of a function is that multiple of the limit of the function. Scale a function by a constant, its limit scales by the same constant, and so on, right? There are other limit laws as well. But it turns out that all of these have derivative analogs, which I guess should not be surprising because derivatives are defined in terms of limits, and the limits have these nice laws. Okay. So the sum rule for derivatives says that if you have two functions, f and g, and they're both differentiable, that is, they both have derivatives, then the derivative of the sum is the sum of the derivatives. So f plus g at x is f prime of x, or f plus g prime at x is f prime of x times g prime of x. Or if you want to write it without the x's, you can just say f plus g prime is f prime plus g prime. That's pretty cool. I mean, I can think of worse ways to have to take the derivative of a sum than just taking the derivative of each term and adding them together. How would you do this? Well, it all stems from the definition of the derivative and the limit laws. What would the derivative of the function f plus g at x be? Well, the derivative of anything is that function at x plus h minus that function at x divided by h, and the limit of that as h goes to 0. Now, f plus g is a function which is based on the two functions f and g, so I can expand f plus g at x plus h to be f plus g at x, f at x plus h plus g at x plus h minus f at x plus g of x. Okay, and now I'm kind of in a big mass of symbols here, but what do I remember? I remember that f has a derivative and g has a derivative. So f at x plus h minus f of x divided by h, I know that has a limit. It's the derivative of f. And g of x plus h minus g of x divided by h, that also has a limit. That's the derivative of g at x. So I can break up the limit. The limit of a sum is the sum of the limits, and each of those limits is the corresponding derivative. Okay? So as long as these two functions have a limit, and they do, it's the derivative, then the limit of the sum is the sum of the limits. That is, the derivative of the sum is the sum of the derivatives. Pretty cool, right? This stems from limit laws, definition of the derivative. Constant multiple rule says that if I take a function, multiply it by a constant, its derivative multiplies by the same constant. All right? And if you want to write it without the x's, you can. The derivative of constant times f is that constant times the derivative of f. Okay? Again, how would we do that from the limit laws? I call this a follow your nose proof because you just write down the definition and there's only really one choice to make at each step. What's the derivative of the function constant times f at x? It's the limit of the difference quotient. So let me write down the difference quotient. This particular function is defined to be a constant times another function. So I can multiply that constant times that function value. The constants are not going to have any effect on the limit. Well, they're going to scale the limit. They're not going to change the fact that the limit exists or not. So you can pull out that constant. And the limit that's left is precisely the limit of the difference quotient for f. And so that would be the derivative of f. Okay, and there you go. So the derivative of a sum is the sum of the derivatives. The derivative of a constant multiple of a function is that constant multiplied by the derivative of that function. And if you put those two together, then you can also prove that the limit of the derivative of a difference is the difference of the derivatives. Okay, so that means we can do derivatives of complicated functions like this. This is a polynomial function. But if you think about a polynomial, what's a polynomial? It is sums and of multiples of powers of x. And I know how to take the derivative of a sum, and I know how to take the derivative of a constant multiple, and I know how to take the derivative of a power function. So I should be able to put all that together to take the derivative of this polynomial. So, well, what did we do last? When we constructed this function, did we multiply? Did we scale? Did we subtract? Did we add? What did we do? What's the outermost thing that's being done? Maybe I haven't asked this question right. If I'm constructing this function, I'm making it out of pieces and combining the pieces in a specific way. And what's the last bit of glue which connects the pieces of this function? The last operation that I use when building this function? Addition and subtraction. Good, thanks. Thanks for understanding the question. No. So the first thing I'll do when I'm taking the derivative is I'll apply the sum rule to each term in the function. So the derivative of 2x cubed plus x to the fourth minus 17x to the 12th plus 37 is the derivative of 2x cubed plus the derivative of x to the fourth plus the derivative of negative 17x to the 12th plus the derivative of 37. So do we agree about that? Because it's a sum of a bunch of functions, and the derivative of a sum is the sum of the derivatives. Now, these are still slightly complicated functions, but not so bad because they're constant multiples of other functions. So the derivative of 2 times x cubed is 2 times the derivative of x cubed. The derivative of x to the fourth, I'm just going to leave that by itself. The derivative of negative 17x to the 12th is negative 17 times the derivative of x to the 12th. And the derivative of 37, well, 37 is a constant, so its derivative is 0. At least I've got one thing that's happening. Okay? Now, the powers that I have here are all nice whole number powers, and I proved the power rule for those. So I can substitute in, for the derivative of x cubed, 3 times x squared. The derivative of x to the fourth is 4 times x cubed. The derivative of x to the 12th is 12 times x to the 11th. And 0, I'm going to stop writing plus 0. All right, so now I'm pretty much done, except I can multiply my 2's and my 3's and my 17's and my 12's, and I get 6x squared plus 4x cubed minus 204x to the 11th. You guys all knew that 17 times 12 was 204? Right. Okay. So if you're seeing this for the first time, this looks a little bit like magic, right? You've got powers, and you bring them down, and you let them multiply, and then you just sort of write it all down, and boom, you have derivative. Once you practice it a little bit, it does start to become a little bit more routine. Right? There's a process where you don't have to do it all the way, step by step, carefully. You can say, okay, this is a 2 times x cubed. I'm going to pull out the 3. That's going to be 3 times 2, so I'll write down 6 and subtract 1 from the power, leaving x squared. Okay, with a little bit of practice, it does start to become easy. Other questions about that? About this differentiation process? Okay. All right, next we're going to move to derivatives of sine and cosine. Sine and cosine are definitely not polynomial functions, right? They're not even rational functions. So derivatives of those functions are going to be more complicated than derivatives of polynomial functions. But maybe we can still find rules for computing derivatives of them. And how would we find a rule for computing the derivative of sine? Well, just like all of the other functions that I've been computing the derivative of, the first thing to do is write down the definition of the derivative and try to simplify that difference quotient. Okay, so I want to find the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. Right, because that's f of x plus h minus f of x divided by h. Now, ordinarily, what I was doing in the previous examples was that I was finding either a way to expand that f of x plus h or to factor f of x plus h minus f of x. Okay? So let me try to expand sine of x plus h. One thing you might guess is sine of x plus sine of h. but that's actually not true. Sines don't behave that way. How do I expand the sine of x plus h? Anyone know? Okay. Anyone remember that they once knew a trigonometric identity for the sine of the sum of two things? Do you remember it? Did you once know it? Okay. That's one of them. Sine of 2x is 2 times sine x times cosine x. And that's a special case of sine of the sum of two things. Okay. So if you're dozing off, I think you want to pay attention at this next point, because I'm going to do something on video that I've never done before. I've done it always in class, but I've never done it on video, so I'm a little bit nervous now. So the trigonometric identity for the sum of two angles goes like this. Sine of a plus b is the sine of a times the cosine of b plus the cosine of a times the sine of b. Likewise, the cosine of a plus b is the cosine of a times the cosine of b minus the sine a times the sine of b. Okay? So anyway, like I said, do you remember knowing this at one time? Okay, it's coming back. So in psychology, they talk about mnemonics, and mnemonics are a way to help you remember something. And I don't know if this is a theorem in psychology, but it stands to reason that the dumber the mnemonic, the easier it is to remember. Okay? So when you look at these two trigonometric identities, you think, how am I going to remember them? Well, they have a basic structure to them. One is that there are two terms, and each of them is one trig function evaluated at a times another trig function evaluated at b. And then you do it again, right? Something at a times something at b. Something at a, something at b, something at a, something at b. So you don't really need to remember the a's and the b's. You just need to remember which functions you're doing, right? So you've got a sine and then a cosine and then a sine, cosine, a cosine, a sine, and a sine. So here we go. This is your mnemonic, and it comes in a musical form. Very musical day. I'm going to sing this trigonometric identity. Are you ready? Are you sure you're ready? This is going to be on the internet, you know. All right, here we go. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. You want to hear it again? Sine, cosine, cosine, sine, cosine, cosine, sine, sine. Like I said, the dumber the mnemonic, the easier it is going to remember. Now, there's one thing I haven't covered in the song, and that's that there's a plus sign here and a minus sign there. So for that, I have the extended version of the trigonometric identity song. And it goes like this. Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. It's the S-I-G-N. You change the sign in the last part. Okay, so now you remember that, right? So I learned that at summer camp from a guy who lived in New York City. He's the first person I met who lived in New York City. You might wonder what we're doing in summer camp, singing trigonometric identity. It was a summer camp for engineers, engineering students. Okay, so questions about that? Is that relevant? Well, I had the sine of x plus h. So that means I can take sine of x plus h as sine, cosine, cosine, sine. Sine x, cosine h, cosine x, sine h, and subtract sine x. Okay, does that help? Well, at least now this term shares a factor with this term, right? I have sine x and sine x. So I can factor out sine x from those two terms. And this one I can't factor out anything, but I can at least break it up a bit as sine x times cosine h minus, well, sine x times 1 plus cosine x times sine h. Now, when I look at those two things, I realize that the limit as h goes to 0 does not depend on the sign of x. This is sine of x, and this is h going to 0. X and h are independent things. So this is basically a constant as far as h is concerned. Likewise, cosine is a constant as far as h is concerned. So I can pull those out of the limits. And what I have is the limit as h goes to 0, cosine h minus 1 over h. And the limit as h goes to 0, sine h over h. Okay, now it so happens that we've studied limits exactly like this, right? This was thoughtful preparation by Jimmy Stewart in section 1.4, we did this limit, and we did this limit. And what was this limit? The limit as h goes to 0 sine h over h. That one is 1, and this one, 0. Both of them, notice both of them are indeterminate. They're both of the form 0 over 0. This one was 1. This one is 0. Okay, and there was a nifty picture that we did that proved all that. You might remember it also used the squeeze theorem. Okay, so what that means is that we can evaluate the limit now. Sine of x times 0 plus cosine x times 1. And that all adds up to cosine x. So there you have it. The derivative of the sine function is the cosine function. All right, pretty cool. Questions about that? So if you graph sine and then you graph cosine, you can totally believe that the cosine is the derivative of sine. Because where is the sine function, that's the function graphed in blue here, where is it having horizontal tangents? Well, right here, you can see that if we drew a tangent line to the curve here, it would be horizontal. What's the slope of a horizontal line? 0. The cosine is 0 at that very place. Down here, we have a horizontal tangent as well. And again, we have a cosine of 0. So the fact that cosine is the derivative of sine, you can believe by looking at the graphs of these two functions. Now, what about the derivative of cosine? Well, if you look at the graph of cosine, you see that it has sort of the same relationship with sine, where the cosine has horizontal tangents, such as here and here and here. Sine is 0 here and here and here. Okay. So you might guess that the derivative of cosine is sine, and you would be wrong, but not that wrong, because if you look again carefully at the relationship between cosine and sine, you see that, for instance, right here, cosine is an increasing function, and the derivative of an increasing function has what sign? Positive. Sine here is negative, so it's not the derivative of cosine. Here, cosine is decreasing, and sine is positive. So again, it's not the derivative of cosine, but it's actually the opposite, because everywhere cosine is increasing, sine is, everywhere cosine is increasing, sine is negative. Everywhere cosine is decreasing, sine is positive. So sine is behaving kind of like the derivative of cosine, but actually the complete opposite of the derivative of cosine, opposite in the negative sense. So what that tells us is that the derivative of the cosine function is the opposite of the sine function. Derivative of cosine is negative sine. Okay, that looks good. Let's do that out with the definition. The derivative of cosine is the limit as h goes to 0, cosine x plus h minus cosine x over h. Okay. And again, we expand that cosine x plus h term. Remember that with the cosine, we go cosine, cosine, sine, sine, sine. And then just like before, I will have a cosine x times cosine h and a cosine x times 1. So I can pull those to the side and factor out cosine x. And the other term is sine x times sine h. So I can break it apart, pull out the factors which do not depend on h. It's cosine and sine in this case. And then evaluate these limits of the trigonometric quotients. Cosine h minus 1 over h, again goes to 0. Sine h over h, again goes to 1. And so I'll have cosine times 0 minus sine times 1. Okay. Cosine x times 0 minus sine x times 1. Oops. So that's minus sine. So if you're trying to remember, where does the minus sign come in this rule? That the derivative of cosine is not sine, but minus sine. It comes from the minus sign in the trigonometric identity. Okay, that last sign in the cosine identity gives us that sign in the derivative of cosine identity. All right? Okay, so I threw a lot at you today, and apparently at ultra-high speed, because I'm done a little bit early, but that's good. What have we learned? We've learned the power rule. We've learned The derivative of a sum is the sum of the derivatives. The derivative of a multiple is that multiple of the derivative. The derivative of sine is cosine. The derivative of cosine is the opposite of sine. And now we've increased millionfold the number of functions that we can differentiate easily.